Welcome to yet another class today. I'm Dr. B and we're going to be discussing something very interesting today, and that is hybridization. So we're going to look at that today. Hybridization. Hybridization. Quite an interesting topic to talk about. I want us to know that the term hybrid is not a new thing and shouldn't be a new thing to us. Of course, we have been hearing about conferences that are hybrid. When we said conference are hybrid, it means that you could attend the conference in two ways. It's either you attend the conference by not going there and using your social media platform or handle to watch, or you attend by going there physically. So, but the important thing is that whether you watch it on phone or through your laptop or you attend physically, you are attending the same conference. That is what hybridization, a hybridization means. So, but talking about hybridization in chemistry, what do we mean? I want us to know that there is a formation of a new atomic orbitals that has different energies and different atomic, different bond angles and bond lengths from the original orbitals that we use in forming them. Okay, this very process that involves the mixing of two different atomic orbitals but from the same energy level, that is talking about the same shell, atomic shell, to give rise to this new hybrid orbital is what we term hybridization. Let me repeat myself. You can pick two different or more than two different atomic orbitals with the same or equal energy, and you mix them to get a new um, orbital that will have different energy and different bond angles and bond length from the initial ones that you have used to mix. That process is what we describe as hybridization. But I want us to know that hybridization is just a topic that's a follow-up from what we call the valence bond theory. And the valence bond theory help us to understand the nature of the bond angles, the bond lengths, and the geometry of what of certain orbitals. And today we are going to look at that. But it's important for us to also remind ourselves that we have various types of hybrid orbitals, and we have the SP, we have the SP2, we have the SP3, we have the SP3D, the SP3D2, and the SP3D3 are hybrid orbitals. These are the major hybrid orbitals that we have. And we have the SP, the SP2, SP3, SP3D, SP3D2, SP3D3 hybrid orbitals. That means that they involve what? They involve the mixing of S and P orbitals of the same energy to get new hybrid orbitals. And this one involves the mixing of S, P, and D orbitals at different proportions to obtain new hybrid orbitals. Now, that will link us to discussing, at least today, we'll talk about these three, the SP, SP2, and SP3 hybrid orbitals. Now, the question is the SP hybrid orbitals or SP2 hybridization. We know very importantly the importance of hybridization, that it helps us to do what? To be able to ascertain, most importantly, geometry or the shape of orbitals or molecules. And then we also have to use the hybridization to also obtain the bond lengths and then the bond angles of different atomic orbitals. Now, the sp orbital means that there is a mix of what? The s orbital and the p orbital of the same energy to form the hybrid orbital you call the sp orbital. Now, that means that you initially we had discussed something concerning shapes of orbitals when we discussed the work of Schrödinger, and then we're able to talk also about the principal quantum number and the azimuthal quantum number, which we said it describes or the shape of molecules. Now, of orbitals. Now, the sp hybridization can also be called the diagonal hybridization. That is, say, you can call this also as the diagonal hybridization. So sp hybridization can also be called diagonal hybridization, and that means that you have the s orbital, which we have the xyz, which is the direction of movement or flow of the electron, which this is the s orbital, one s orbital interacting with what? Interacting with one of the p orbitals. This is the xyz. So it means that one of the s orbital is intermixing with one of the p orbitals, all right, and then it will give you an sp hybridized orbital, and that sp hybridized orbital, it's something like this. Okay, so it's not like this. This is just it. This is an sp hybridized orbital. You can see that it is the mixing of the one s orbital and one p orbital of the same energy or the same shell. When we say the same shell, we mean the same energy of an atom, to give you what? To give you two separate orbitals that mix together and give you the sp hybridized orbital. Very importantly, now you have been able to know or understand the shape of the sp hybridized orbital. And I told us that one of the importance of the valence bond theory that links hybridization is that you will be able to learn the shape of what? An orbital. Now you are able to learn that the shape of this orbital is linear. So the shape is what? It has a linear shape or structure. Has a linear shape or structure. So the sp hybridized orbital has a linear shape or what? Structure. And you will also be able to learn the bond angle. And the bond angle here is what? The bond angle here is 180 degrees. So you see that for an sp hybridized orbital, there is what? A linear shape, a linear structure or geometry, and there is a bond angle of 180 because it is what? Linear. Remember that linearity goes with what? 180. That now, having understood what an sp or a diagonal hybridization means or imply, and how it is formed, and what the shape is, and also what the bond angle is, what are the possible examples of those particular compounds that exhibit the sp hybridization? Now, all the compounds of beryllium, they do what? Exhibit the sp hybridization. So it means that beryllium fluoride, okay, all of them, beryllium hydride, all of them, they exhibit the sp hybridization. Also, all the compounds that possess double carbon-carbon triple bonds also do what? Exhibit the sp hybrid. That means that compounds of beryllium will always have structures in this format and have a bond angle of 180. And then also compounds that has double carbon-carbon what? Triple bonds, like what? Ethyne. Compounds that has, let me say, C2H2, like ethyne, also do what? They exhibit characteristics of the sp hybridization. Now, in an sp hybridization, the characteristics that the new compound, the new hybrid orbital will exhibit is going to be what? 50% of the s character and 50% of the p character. That means that this is 50% of s character and 50% of the p character you will be seen will be noticed in an sp hybridized orbital. That is to say, in this kind of compound, you'll be expecting to see characteristics of 50% s orbital and 50% p orbitals. This is for the sp hybridization or diagonal hybridization. Now, can we take a look at the SP2 hybridization? Let's look at the SP2 hybridization. Now, looking at the SP2 hybridization, it is just something a little away from the SP. So if we see the SP2 hybridization, it can also be called the trigonal hybridization. A trigonal hybridization. See, so the SP2 hybridization can also be called the trigonal hybridization. It is very simple. So in this one, in SP2 hybridization, one of the s or atomic orbital and two of the p atomic orbitals of the same shell of an atom or the same energy of an atom will mix to give you a new orbital called the sp2 hybrid orbital, and that orbital will look like this. So it gives you three orbitals that join to form one. So it will look this way, and then it also look this way. Sorry, it's also look this way, and it looks this way. Now this is 1s, 1p, and 1p. So there are 2p orbitals and 1s orbital. But the important thing is that they possess the same energy. It doesn't matter what forms hybridization. Both the fully filled orbitals and the half-filled orbitals can hybridize, provided they have the same energy. And again, they can also hybridize provided they are in a mix, because isolated orbitals cannot hybridize. You must also understand that. So this is sp2 hybrid orbitals. Hybrid orbital. Now this means that this is 1s, 1p, and 1p. So you can see that in this one we can be able to determine what is the shape of this one. Now look at this, and then look at this, and look at this. Did you see? So you can see that it is what? A trigonal planar. So you can see that the shape of this is what? A trigonal planar orientation or structure. You see? And then of course the bond angles around here, each of them have the same bond angle of 120 degrees. 120 degrees, 120 degrees. This is their bond angle. Now you can see that we have an sp2 hybridized orbital that is formed from one combination or mixing of 1s and 2p's orbitals or individual orbitals with the same energy. But at the end of the day, you will have different energy for this new orbital that is formed called sp2 orbital, and different bond lengths or bond angle, and of course bond length as it is. Now with this we can understand that we have also some examples of compounds that exhibit sp2 hybridization, and one of those particular compound is the compound of boron. That means all boron compound exhibit sp2 hybridization. So boron trifluoride, boron trihydride, all the compounds of boron, they exhibit sp2 hybridization. That means they will possess a trigonal planar structure and also a bond angle of 120. Again, all the compounds that exhibit or rather contain the carbon double bond also show SP2 hybridization. So compounds that has this also show what? Also show they also show a typical, they also show a typical what? All the compounds that have carbon double bond also exhibit SP2 hybridization. Quite interesting. All right, how about the SP3 hybridization? That would end whatever our discussion here is for this class today. So the SP3 hybridization, how does it look like? I want us to know that the SP3 hybridization can also be called the tetrahedral hybridization. Tetrahedral hybridization. That is the SP3 hybridization. Can also be seen as what? Tetrahedral hybridization. But it's important for us to know that this hybridization make use of one s orbital, okay, one s orbital and 3p orbital. Now there is something we have skipped in our SP2. Remember we had said that for an sp orbital there is 50% by 50% of what s and p contributions to their character. So for sp2 there is rather 33.3% and 66.6% of the s and p contribution. But for the sp3 there is 25% contribution of s and 75% contribution of p character for an sp3. We must make sure we take note of this because the proportions are not the same in the mixing process. So for sp3 or tetrahedral hybridization, there is one s orbital mixing with 3 p's orbital, and it will definitely have a structure of this nature. So we have this, we have this, we have this, we have this. So in this format, we'll have this to this, to this, and to this. Now we have this and we have that. So this is 1s, this 1p, this 1p, this 1p. This is how the structure of an sp3 hybridized orbital looks like, and this structure can be called the tetrahedron structure or shape. From here you have the name, the tetrahedron structure or shape, and of course the bond angle for each of these you see here is it's about 109.5 degrees. So each of them have 109.5 degrees bond angle, and this is a tetrahedron shape. So contributions that are made for each of these orbitals with the same energy, it's 25% of sulfur and 25% of 20% of the s orbital and 75% of the p orbital character will be shown in this tetrahedron structural shape of an sp3 hybridized orbital. Common example that you can see here are every compound that possesses carbon single bond. So all the compounds that, for example, C2S6 is an example of a compound that exhibits sp3 hybridization. Next time we meet, we are going to look at the sp3d hybridization. I'm sure you enjoyed this class of today talking about hybridization, but before you go, you have to take home these are the essence of hybridization, of the mixing of different orbitals is to be able to ascertain structure, that is orientation or shape of molecules and also certain orbitals, and then to ascertain also the bond angles and bond lengths of certain orbitals and molecules, and that it is a link to the valence bond theory. So you need to understand that. Again, you must also know that both fully filled and half filled orbitals can hybridize, especially when in a process of mixing, that isolated orbitals cannot hybridize. You also have to know that it is a combination of orbitals at the same energy level. Until next time, do not forget to share, to like, to subscribe to my channel, to also comment. It is bye.